The AIDA-2020 project brings together more than 40 European research infrastructures in the field of detector development. The transnational access activities support small teams to carry out experiments and tests at 10 of these institutes. One of them is the MC40 Proton Light Ion Cyclotron at the University of Birmingham in the UK.
I'm Professor Phil Allport at the University of Birmingham. I'm the person who's responsible for coordinating the Transnational Access under AIDA-2020 to the Medical Physics Cyclotron at the university in collaboration with the Particle Physics Group and the Medical Physics Group. We support use of the MC40 Cyclotron for irradiations using protons or light ions with currents from picoamps up to microamps. This means that in minutes to hours, we can reproduce the doses expected after 10 years right next to the collision points at the high luminosity upgraded CERN Large Hadron Collider. For the AIDA program, we take samples from around the world and irradiate these to the required doses, operating at the chosen irradiation rate and operating temperature. Samples are delivered to Birmingham for us to prepare, scan at low temperature in the beam while measuring the proton rate, and then to check the integrated doses afterwards with radioactive foils. The beam comes through here, and before we do anything, we check the beam with the Faraday cup, and once we make sure that we've got the beam settings set up and we've got the calibration right, then we can put the samples inside the box, which is suspended from the lid here. You can see it's an insulated box which is kept cold with liquid nitrogen which is evaporated from the plate at the bottom. So we put the sample on these aluminium plates in front of the window. You can see there's a window at the front and the back for the protons to pass through. We close it. We spend about an hour bringing it down to a temperature of about minus 35 to minus 40, and when everything is ready, then we move the box back up into the beam and start the scanning for the irradiation. The radiation field is defined by the collimator, which is 1 by 1 centimetre, and devices in the cold box can be scanned through the beam for areas up to 20 by 20 centimetres. We can scan with microamp currents to reach 10 to the 16 neutron equivalent per square centimetre doses in a few minutes, or down to picoamp currents to study dose rate effects. The energy range of the cyclotron is up to 36 MeV, so energy losses will need to be considered for thicknesses more than a few hundred microns. We can either irradiate scanning at up to 4 millimeters per second or at a fixed position with temperatures down to minus 50 degrees centigrade. Measurements with nickel foil show we can typically predict the delivered dose to better than 10%. Samples can be mounted and measured if required at Birmingham using its new suite of clean rooms. Wire bonding and probing with full device characterization is available in case samples are too radioactive to ship.